Okay, I want to tackle an ALEKS problem like this one. It's asking us to consider this phosphorus tetrachloral cation. It's going to ask us what is the central atom. We should be able to get that one pretty easy. How many lone pairs are around the central atom? We'll have to do some Lewis dot structures to get that. What is the ideal angle between the phosphorus chlorine bonds? And it's going to ask us to compare it to the ideal angle. Would you expect the actual angle to be, in this case, about the same, bigger or smaller? So we'll just have to consider the effect perhaps of some lone pairs or some double bonds. And so let's go ahead and let's do this Lewis dot structure for PCl4 plus. And so I'm going to go ahead and draw the Lewis dot structure for PCl4 plus. Let's do valence electrons. So for phosphorus I have 5 valence electrons. For each of the chlorines I have 7 plus times 4 is going to be 28. But then I want to subtract 1 because I have that plus charge. And so that is going to give me a total of 32 valence electrons I have to consider when drawing the Lewis dot structure of PCl4. And so let's do P, Cl, 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 and so I have PCl4. I have 32 electrons that I have to count for, so let's distribute my valence electrons around the chlorines to generate the octets, the octets right here. Okay, so PCl4 plus, let's count valence electrons. Each of these units has 8 valence electrons. I have 1, 2, 3, 4. So I have drawn the Lewis dot structure for PCl4 plus because it has 32 valence electrons. All my octets are taken care of, and I feel really good about this. And so let's go back. Before we go back, I want to talk about this. Notice how each of these is a single bond right here. There are no double bonds. There are no lone pairs at all in this particular molecule. This happens to be extremely nonpolar. If we were to look up our tables, we would find that this is, in terms of an electron group, this is tetrahedral. And then for the shape itself, it is also tetrahedral. I have that memorized, and I have that memorized from a table such as this, where, if you remember, our AXE, where A is the central atom, X is the number of atoms surrounding the central atom. In this case we have 4 chlorines, and E is the number of electron pairs around the central atom, which is 0. So this is AX4. I have A is the P, the X's are the 4 chlorines. And so if I go back to the notes, which I have memorized right now, then I know that this is tetrahedral. When I go to my tetrahedral, I notice that AX4 is tetrahedral. The ideal bond angle is 109.5. And since there are no lone pairs, if you look at the effect of this lone pair right here on the trigonal pyramidal, then you see that that lone pair makes those angles, notice how it's less than sign. It would be, if you did have a lone pair, which we do not, but if you did, you would expect these bond angles between these atoms to be less than 109.5. And between, if you had 2 electron pairs, lone pairs around that central atom, again you would expect these bond angles to be less, because that electron density is pushing those bond angles to be smaller. And so let's go back to ALEKS and let's just answer the question here. So what is the central atom? We know that it is phosphorus. How many lone pairs? We know that it's 0. What is the ideal bond angle? It's 109.5 degrees. And compared to the ideal angle, would you expect the actual angle between the phosphorus and chlorine bonds to be? it is going to be about the same, because we just, in our structure, we don't have any lone pairs or double bonds or triple bonds that are changing the ideal bond that we see in our particular molecule. So if we were to submit that then to Alex, then it should tell us that we are correct. It's always a risk when you're the professor doing these. And so we did get it right, and so I hope to do one where we actually show that maybe the bond angles will change, and I'll look to do that in another video.